In our universe, all things are driven by energy. Energy powers our sun, our environment, our society, even our bodies. Energy is life. New and profound advances in science and engineering are allowing us to harness this energy abundance in marvelous new ways. To create clean, affordable, and reliable energy for all Californians. The SoCalGas Research Development and Demonstration Program has enlisted an incredible team of experts in science, engineering, industrial technology, and environmental policy to identify, build, and implement these transformational technologies throughout society. Collaborating with the world's top institutions, we have deployed over $73 million on hundreds of groundbreaking projects over the past 5 years. Hyatt Hydrogen, which could enable transporting hydrogen through existing infrastructure to power fuel cell vehicles and facilities. Doosan Mobility Innovations hydrogen drones that have 4 times the flight capacity of lithium-ion powered alternatives. And hydrogen-powered yard trucks that can move massive shipping loads for 20 hours per day with 0 emissions. These revolutionary projects are saving energy, reducing emissions, and improving air quality, as well as increasing energy safety, reliability, and affordability for all. At SoCalGas RD&D, we believe in clean energy abundance, so we are sharing this pivotal research in order to deploy these innovative technologies across the world. Because energy is life. And we believe a clean energy future will bring a better future to everyone. SoCalGas, Research, Development, and Demonstration. Learn more at www.socalgas.com/RDD.
Good morning, everybody, and welcome to the SoCalGas RD&D Research webinar. My name is Ed Newton, and I am the Gas Engineering Programs Manager at SoCalGas. For today's webinar, we will be welcoming Daniel Ursoy with Element Resources to learn about the exciting work that we have conducted at SoCalGas in developing company-specific emission factors for customer meter leaks and emissions. Before we begin, I'd like to walk everyone through the GoToWebinar toolbar that should be visible to all the attendees. Please enter your questions in the question box drop-down. You'll notice that there's a few different drop-downs in the menu, and one of them is titled Questions. We'll be reviewing them during the Q&A session after the presentation. And during the Q&A session, we'll also be opening up the question for verbal questions, or the discussion for verbal questions. Click the raise the hand icon to be called on during the Q&A. The SoCalGas RD&D program is divided into 5 areas that span the entire energy supply chain, from low carbon resources, where they look at renewable gas production, to gas operations that focuses on the technology development of the operations side of the gas supply chain, to ultimately where we use the gaseous fuel from clean transportation, clean generation, and customer end use applications. I would like to also share our commitment to the community. We have a link in the deck to our equity engagement roadmap to share with you the things that we are doing within the community from a research perspective. And we would also like to stay connected with our research community and stakeholders. And there are a number of ways that we do this with our RD&D webpage, our RD&D LinkedIn page, and our newsletter. Attached is a sample of the RD&D webpage with a QR code that will take you to that link. Our RD&D LinkedIn webpage, also with a QR code, where you get additional information and articles as they are published. And our RD&D newsletter that comes out periodically, again with the QR code for that information. In addition to our traditional research program, we also are involved in our gas emissions abatement program, which is funded under a separate regulatory proceeding aimed at reducing natural gas emissions from the distribution, transmission, and storage portions of our operation systems. California leads the nation in setting climate goals and policy. We have the governing law under SB 32, which requires a 40% reduction in GHG emissions from 1990 levels by 2030. And then under the SB 1371 Senate bill and resulting regulations, the goal that was established was to reduce natural gas emissions by 20% by year 2025 below 2015 baseline levels, and 40% by year 2030. So within that regulatory proceeding, one of the areas of focus of emissions from the distribution portion of our system is our customer meter facilities. Originally, back in 2015, the emission factors that were proposed within the program were leveraging the national emission factors, which were developed in prior years from national studies that measured emissions from the customer meter facilities. And it was a factor that was developed that applied on average nationally to all the customer meter facilities across the nation based on those studies. As a result, the emission factor estimates that are applied on a per meter basis would approximately result in an annual emission rate of 0.15 MCF per meter. And the SoCalGas meter count over the years from the 2015 baseline increased about 5% year over year. As we transition from these population-based national average emission factors to using leak-based factors that were better representative of the true emissions from the individual LDC operations, we leveraged the statistical analysis of local system data. And by shifting to the leaker-based approach, this allows for us to realize emission reductions without having to reduce system infrastructure. SoCalGas has been involved in many of the national studies that were conducted in order to develop those emission factors. And so since the early 90s, SoCalGas, because of that involvement in developing the national emission factors, we understood the steps necessary in order to develop company-specific emission factors. But we also had to develop additional approaches in order to shift from a facility-based factor to a leaker-based factor. And so for the customer meter category of emissions, this is what we have done under the SB 1371 research funding to develop the approach and the rigor that's necessary in order to develop the company-specific emission factors. We have published our research reports, and on this page you can see the link to the research reports that have been published on our company website. We have also published an article through Environmental Science and Technology, and the links to the article and the supplemental information to the article are also provided on this page. So without further ado, I'd like to introduce the folks that have been involved in developing the environmental and science paper. We have, of course, Eric Rodriguez, who is the gas emissions RD&D team lead, and Eric managed the field portion of the study and the employees that were and the research contractors that were out conducting the work in the field. We have Mr. Daniel Ursoy, who is the founder and principal engineer with Element Resources. And Daniel is the founder and principal engineer of Element Resources, which provides technical support and over 30 years of comprehensive professional experience in environmental emissions research, risk and integrity management, advanced statistical and probabilistic analysis and modeling, and engineering safety and operations research and data analysis. Dan's past operational and research leadership roles include being part of Gas Technologies Institute, Energy Delivery and Integrity Management sector. And while Dan was with GTI, he was involved in some of those national studies and state studies where we looked at the emissions from customer meters. And when he started his own business, there was a natural transition there between us and Dan at Element Resources. He was also involved in the University of Illinois Material Engineering Group, Argonne's National Labs, Energy Technology Division, and the U.S. Navy's 7th Fleet, the Nimitz Battle Group, and Western Pacific Tactical Services Command. Dan has degrees in engineering, metallurgy, materials engineering and corrosion, and nuclear operations. And Dan holds numerous patents, dozens of technical publications, and is a lifetime member of the Veterans of Foreign Wars. In addition, Dr. Brian Lamb joined us as we started to complete the work, and we were publishing our reports. Dr. Brian Lamb was one of our peer reviewers for the original research study. And then as we went into publication with environmental science and technology, Dr. Brian was part of the team that put together the publication article. And Dr. Lamb is a Regents Professor Emeritus in the Laboratory for Atmospheric Research and the Department of Civil and Environmental Engineering at Washington State University. He has been at Washington State University since 1979, where he directed a wide range of atmospheric chemistry, pollutant transport, and air quality field programs. Dr. Lamb has been involved in national programs to measure methane emissions from natural gas systems and landfills. In 2013, he directed a series of natural gas studies focused on distribution pipeline leaks and facilities as part of a series of natural gas supply chain studies sponsored by the Environmental Defense Fund. His publication record includes more than 200 peer-reviewed journal papers. Dr. Lamb received his PhD in 1978 from the California Institute of Technology and his BS in chemistry in 1973 from Idaho State University. And myself, just a little bit of background. I've been in the natural gas industry for 39 years, with SoCalGas for 22. I've managed the distribution integrity management program and the research programs for gas operations and gas emissions for SoCalGas. And I led the development of the emission factors, both for the customer meters and for our below ground customer meters, which will possibly hold a future webinar to share the results of that work. And so with that, I'm going to turn it over to Mr. Eric Rodriguez to share a little bit of information about the field work before we turn it over to Dan for where we get into more of the technical analysis of the data. So Eric, I will turn it over to you.
All right, thank you, Ed. So I'm going to go over here very quickly before Dan gets into the fun of the statistics on what we did from a sampling perspective. So we grouped our entire service territory into 9 meta-districts, each with approximately 11% of the total meter population. We did this because we wanted to get a non-biased, proportional, stratified random sample as part of this project. We randomly sampled leaks that were identified by our survey team within these meta-districts, and we found about 425 leaks that we sampled over the course of this project. Additionally, we looked at meters that were classified as non-leaking or no leaks were found by the survey team, and inspected those to see if there were any smaller leaks that were present that are not captured by the current survey process. We defined that as any emitter that had a 100 ppm methane concentration when analyzed with a fine-tipped probe. And from 206 meters that we looked at, where we scanned every single threaded connection meticulously, we ended up finding 60 of these non-detected leaks. I will mention on that table on the right, you'll see that Meta-District A has a larger number of leaks measured than the rest of the districts. And that is because Meta-District A is the first district that we sampled during this project. And it's where we developed the method and process that was carried into the other districts. All of the MSAs within our system can be categorized into 4 groups. From a survey perspective, we have meters that are surveyed within that year as part of a compliance survey, and meters that are not on that current year's survey cycle. Leaks that are detected by the survey process are in that detected leaks bucket, and they can be classified as hazardous or non-hazardous. And then leaks that are present on meters that are not surveyed for that year are estimated based off of your known leak rate from your surveyed portion of your system. And those go into an unknown leaks bucket. Additionally, as I mentioned in the previous slide, there are leaks that are not detected by the survey process. These are, again, classified as leaks where the methane concentration is greater than or equal to 100 ppm when scanned by a fine-tipped point probe sensor. And then lastly, you have the final bucket, which is the remaining meter sets, which have no leaks or leaks that do not meet that threshold criteria or any of the other criteria. And on this slide, I have an example, some photos of the sampling that the team performed. You can see in the top left there, there's a high flow sampler, which is pulling in a sample of air that has a flow meter attached to it. And then a methane concentration sensor measures the concentration of the methane in that airstream. And you can perform the math to estimate the total natural gas leak rate that's coming through. These adapters that we used are shown in that second picture there that we placed around the leaking component. We had a variety of adapters that could be used for the various components and configurations on the meter sets. We were also checking bubble sizes as shown there, measuring bubble size, and I'll let Dan get into the mathematics on that. And finally on the right there, I have some photos showing the fine-tipped probe scanning procedure where every single threaded connection is meticulously scanned. And so now that I've given you a little bit of a preface there, I'm going to pass it over to Dan Ursoy so that he can go through the statistics.
Thanks, Eric. I'm going to run through probably a pretty good bunch of slides here, and we'll just step through them. And we're going to, this first slide, I'm going to spend a little bit of extra time on. This is kind of the overarching statistical basis and the technical methodology. Now that Eric and Ed have kind of laid down the broader overview operationally and historically of why this study was done. So the purpose of this study, as Ed already had talked, it really is to use the best possible statistical probabilistic methods to develop the company-specific natural gas emission factors, as opposed to just doing a population count of your meters, let's say, Can we do one that's based on your own company's data, not national data, that uses refreshed and updated emission factors based on the leak categories, as opposed to one, I guess you could say, one size fits all national number that you just multiply your meter set by, which doesn't give you really any flexibility to determine your reduction in emissions. It's just, you're just linked at the hip to your meter count. And so this, the figure on the right here, it's broken into 5 blocks, and I'm going to step through the first 4 in detail, and then Eric's going to take a little bit of the 5th block, which is kind of the wrap up of our discussion, or we'll just hit down on the questions most likely. So Ed already talked about this first. If you look at the numbered list here, 1 through 5, those are the numbered blocks on the right. And we did leverage like the CARB, OTD, other national studies, and in particular the SoCal studies, because you'll see on the next slide, we did a precision and sample size analysis so that we would go into this study with a statistically meaningful sample. Not only that it's not biased, but that it's also large enough to get you the confidence intervals and level and precision you need. So that's where we pulled the standard deviation estimated from there. The second step of this program was, and Ed and Eric just went over that. That was the non-biased system-wide stratified sample. I'm going to go in detail on the next couple slides on that. And then, like Ed talked about, you'd have operations come in and they say, do I have a leak or not? And then the ones that they say we don't have leaks on are the green box. And when you come down here to number 3, we did that sampling, and then research comes in and does their measurements. And so the leakers you're going to see presented. So when I'm talking about leakers, those are the 425 leakers. The non-leakers I don't have any data on because there's 0, right? There's no, so just keep that in your mind. You won't see the non-leakers. But the ones that were non-leakers, that if you were to take a pencil probe, like Eric showed just in the last slide, and you checked for 100 part per million or more, we call those non-detected. So I'll refresh your memory on that. That's effectively looking for, if you will, like a false negative. I don't even want to say that because we were taking what is called non-leakers in the field and just really double check and seeing, and you're going to see this 100 part per million equates to a really low leak rate, because we were able to correlate with a nice correlation concentration versus actual verified leak rate. I will go through the different things that are continuous variables like concentration and leak flow rate, which is the last slide here Eric said. So you're measuring concentration, you're measuring a concentration here, you're capturing the leak flow rate here. This is a categorical variable we're going to go through. It just means it's buckets. So it's foam, it's no bubbles are formed. It's going to be like bubbles, which are bigger than foam. You can go into, I'm not going to go into all the minute detail. That's in the report you can download. And then, or soap couldn't form because it was blown off because the leak is too big. So there'll be categorical variables we're going to go through here by meter type, bubble category, if it's a leaker or non-leaker. The big one we're going to go through is the PHMSA categories for hazardous and non-hazardous. That's how our main categorization really shook out nicely. And then finally, this is the sample, right? I'm going to go through the sample that we took, the 425 to 206, and then we impute that over to the population with analysis, inferential statistics, and probability theory. So I'm going to go through bootstrap, log normal, bootstrap resampling, log normal fitting, Bayesian proportional analysis to break out these 2 buckets, the leakers and non-leakers, out of what Ops calls non-leakers. And then we did a fully uncoupled, really rigorous Monte Carlo analysis to pull all this together to get emissions using population data from SoCal and everything I just talked about above. And then at the bottom, you're going to see that sprinkled throughout. Those are the actual findings of the emission factors and what have you. So before you do a test, right, you need to determine a priori, that means beforehand, what sample size you need. Otherwise, you do all this work and your precision is so bad. I'm not talking about accuracy, I'm talking about precision. How much uncertainty is there? And what are we measuring? We're measuring the average leak rate for a leak, right? We're measuring the emission factor by a category. Let's say a hazardous leak versus a non-hazardous leak. Let's say a leaker versus a non-detected leaker. And you get an average value, but you have uncertainty bands around that, which we quantify as a confidence interval. So to do that, you have to do really a very rigorous precision and sample size calculation, and you have 5 values. You can pick 4 of those and set them, and you get the other one, okay? And you can do that any way you want, but we want to know how many samples do we need in this study to get a confidence level that we subjectively set at 95%. We want to be able to say on our prediction for the emission factors that we're 95% confident, and I'll kind of concisely say this, it's statistically a longer way, that our band would have a 95% chance of capturing the population average on a sample of that size. And we also want to set our precision. Many studies, and I dare to say that some of the national studies that were published did not do this. It's not in the report, and they didn't really think about the precision they wanted to get and the probability of achieving that precision. And that's a shame, because there's some of these anemic sample sizes that you report an emission factor or an average, and you don't really have the precision at the probability of achieving it. I'm going to go over that in a second. So we set our precision at 95% as well, our probability of achieving it, and a precision at a reasonable number that's tight around the average value we're looking at. And finally, you have to put an estimate of your standard deviation, because it's not only the sample measurement, but it's the spread of that through the covariance matrix or the standard deviation. Same thing, mathematically, different form. And we use that from the prior studies. So when we plug all that in, before we did our first sample, we came up, and here's a plot. This will really bring it all home now. I think this is important to go over. We were very rigorous in this study, not only in the random sample we did and a stratified proportional sample, but in this analysis. And you can see here, the bottom line is we needed 141 samples, which is this red dashed line. If I come on the 1.1 skiff for standard cubic feet per hour curve, we'll ignore the other ones, it's just for completeness. And I say I want a 95% probability of achieving my width of 0.17 skiff. And I come here, it intersects here, I need 141 samples, okay? We have 425. And I didn't show on here, and I'm just gonna say a word about it, I didn't show the Bayesian analysis we did for probability. And that's the probability of the proportions we found that were, if you wanna say false positives, but they really aren't. They're just what percentage of the non-detected leaks were above 100 part per million with a pencil probe, fine measurement like that. And we far exceeded what we needed there. We needed like 130, 140 as well on that. And we had well over that at 206. So and I'm going to show in one subcategory, these are for the overall study, we had hazardous leaks, and I have a separate slide for that where we step that down to an 80% confidence level, because they're very hard to find that leaks. That's a good thing. You don't have a lot of hazardous leaks. But that number is going to be 35 you're going to see for that, and I'll go over that later. Okay, so important, the physical assets in the gas industry in above ground and below ground, which we're not talking about today. And I've done a lot of work. I've done projects for CARB, I've done projects for the CEC, I've done projects for the government and for industry. They're all log normally distributed. It's not a surprise, it's not a mystery. That's just the way these leaks are distributed on the system. And if you take the data, we not only did we do a log normal shift and look at it and see and this is graphically, but we did it quantitatively. They're very log normally distributed, very nicely, high correlation, high alkanes, high Bayesian data criteria correlations. And you can see that right here. This is it transformed the leaks, the 425 and then the 60 non-detects that were above 100 part per million. And you can see they're normal here because this is the log normal of the data, but better, this is a really good plot, these quantile normals. And if they're log normal, they follow the line, and you have a little bit of breakout on the tails, which is normal. But they're very well log normal. That allows us to run the ANOVAs using frequentists. We also did non-parametric Bayesian analysis and bootstrap analysis, but I'm going to talk about the regression analysis for sensitivity study later, so I just wanted to go over that. This is all 485 samples thrown together just for an illustrative purpose. We're going to break out just the 425 and the 60 later, but I just wanted you to see this. So this is your cumulative distribution leak rate of 485 samples, and the red is a 2-factor log normal fit. That is fantastic. The correlation here, or the information criteria, is really strong. You can just look at that and say, wow, that's a good fit. It is log normal. And if you take either the data, which is the black dots, or the log normal fit, which is this mathematical fit right here, red, and you look at this, this is the percent, if you will, from 0 to 100% of the leaks that are at this leak rate or less to the left, or at this leak rate or to the more to the right. And a lot of people know this, but I want to bring this home. This is really important if you're paying attention to a few things. These few leaks to the side here, on the right side of the distribution's right skewed, but on the right side of that, if we look at these 2-3 leaks here, 1%, they're like, let's say we have 1% of 485 roughly. So you can do the math in your head, 4 or 5 leaks there. Those 4 or 5 leaks are equivalent to the total leaks you would get from everything to the left. It's no surprise that the largest leaks account for the bulk of your emissions. What's not captured here is how long these leaks are going. So I can add these leak rates up, and I can say that's equivalent to an emissions if they all leak for the same amount of time, because this is a rate, not an absolute value. And we're going to see that this process that SoCal came up with allows them to prioritize, to identify and prioritize these larger leaks faster, pull them forward. And so not only are they benefiting by finding those and pulling them forward, but they can attack them earlier. And it's not just based on an uninformed meter count like the national emission factors are. Okay, I told you I would tell you about this. I'm going to tell you about it. There's one category we're about to talk to. I'm going to go to it on the next slide, I believe. And we break down the leaks into hazardous and non-hazardous as defined by PHMSA. I think Ed mentioned that. And these are harder to get. They're larger leaks, hence they're hazardous, right? And there's other criteria on what makes a leak hazardous. I'm not going into that. The operators know that, and the regulators on the call. And there just aren't as many. So we knew we had to relax that confidence level down a little bit, and we reran the PRSS before, and we said, look, let's go with an 80% confidence level. That's what a bunch of the other studies have done for these smaller sample sets. And what will we need? Well, we'll need 35 samples. And we'll see later that we had 30 from SoCal, and we added 5 in from San Diego, as you'll see in the reports. That's their sister company under Sempra. And that got us up to the 35. And you say, well, how can you add the 5 into the 30? Well, you can. We did a full ANOVA analysis of those leaks, and they're statistically not different. And it's not a surprise. It's the same company, very similar, if not, the same system, and the same operators went out there and did the measurements. So statistically, there was no difference with the P statistic. So we could combine them. I'm happy to announce we actually have more than those 5 now that SoCal's got since we, put this presentation together and published the report. And those are exactly well behaved, just like the San Diego were. So we don't even need those. So the point is moot, and the results will look the same when we swap those out. But I just wanted to point that out. You'll see that in the paper and in the reports if you choose to download the reports. Here's what I talked about. We took those samples and we broke the 425 out into 30, and these don't have the other 5, but into 30 hazardous and 395 non-hazardous. The reason behind this is really important. These are larger leaks. These are fixed on a continuous basis. You don't really wait to fix these, but you're driving to fix these all the time. I'll call it an immediate. I'll probably say the wrong term, but it's just the way it is in the industry. And the non-hazardous are by far the bulk of the leaks, right? And the beautiful thing about this is, as we'll see later, is SoCal has 100% of the population data of their leaks, whatever that is, 50,000 leaks, 10,000 leaks, whatever it is. Every year they have them categorized in these groups. They have to. And so we have perfect population data with no uncertainty. That's very rare. It's delightful when you're doing the technical work to have no distribution. You have an actual value, an actual population number. And you'll see here that these hazardous ones are basically 0.1 to 10 to 100 to 1. That's 1, 2, 3 orders of magnitude. Pay attention to this. There's 6 orders of magnitude of leak rate. And that's normal across the industry, right? It's a log normal distribution. And I'll talk about that later. And here you've got it down to basically 0003, 0001. So you've got, 1, 2, 3, 4, 5, 6 orders of magnitude here, 7, 8 here. That's why this is powerful, separating these out. And if you take that same data and throw it in a box plot, I want you to pay attention to this, because I'm going to show you the bubble categories. You can also try to categorize with a soap bubble test, and we did that. We did it very rigorously, and it just doesn't have the sensitivity, the differentiating power between categories. You have too much indeterminate, too much overlap in the categories. And here you don't have overlap. You have a little bit, but these interquartile, 50% of the data is above this line and below that line. 50% above and below, and 50% of the data is also in these boxes. They do not overlap. You can really discriminate the leak rates between these two groups, and you have 100% of these categorizations every year in the system. This is a beautiful thing for company-specific leak rates. And if we take this same plot I just showed here, right, the same plot, and we instead put the average leak rate and the 95% confidence intervals on, this is your emission factor. Now, my units are standard cubic feet per hour, and that's called SCIF, right? You can equate that to natural gas per hour, and you can equate emissions to MCF of natural gas per year. So don't get too hung up on the units right now, but just understand these are the emission factors for hazardous and not. And why can I say that? Because this is a bootstrap resampling analysis. We take the data at the sample size they're at, and we resample it 10,000 times. Why do you do this? You can't really use frequentist statistics. You kind of, in this case, could use frequentist by doing a log normal distribution, shift transform, but this is the gold standard. Everything we did in this project was the gold standard, statistically, probabilistically, sample size. And we resampled this 10,000 times. We set our bands arbitrarily. We picked off the 95% confidence bands, and you can see these are huge separation between them. And we have a very robust, good data set. It meets our statistical quality that we want for precision. Now, this is separated, the same data, by the way, is separated now by leakers and the non-detected leakers. Remember, there's 425 that leaked. They looked at 206 that they said that didn't leak, and then they put a separate precision pencil probe on looking for 100 part per million, and 60 of those 206, they were above 100 part per million or higher. And you can see they're very much down on this lower end, below 0.1. Many of the leakers are up here. And if we do a CDF plot, a continuous distribution function, you can see it's much lower. This is a log scale, right? So you can see this point was like 0.1 or less than 0.1, and it's separated out here. And these are the averages of these log normal fits here. Okay, so if I do the same thing and we wanted to get these leak analysis of leakers and non-detected leakers, we don't really need the leakers because our leakers are categorized as hazardous and non-hazardous. So these can constitute our emission factors for the leakers. We know 100% population, not only the leakers, but we know from the sample, we know if they're leakers or non-leakers. It's a really subtle point, but important on using company specific, and the PHMSA gives you that ability. those hazardous categories. The non-detects are double 08. So if you look at this, this is 1, 2, 3 orders of magnitude lower than the leakers, these non-detects. And we're going to find out, this is really low, and we'll see the correlation. That's basically what you're getting at 100 part per million. That's a really cool finding of this study, and we'll show you that. We correlated really good data with concentration versus leak rate and published that, and the industry gets the benefit of that. Okay, now, what is this? This is a Bayesian proportional analysis. That's fancy sounding. I'm not going to go into the math with beta distributions and conjugates and how you use conjugates in Bayesian analysis and dumb priors and things like that. You can look in the paper or look in the reports for that. But this is a robust analysis where we say, well, we know that we had 60 out of 206. You can do the math, that's 29%. But we want to get a full distribution around these proportions that if I go all the way back, which I'm going to do, to this slide, what's the likelihood that when we call it a non-leaker, it'll fall in these buckets? And what's our error around that likelihood distribution? Well, we solved that. We used Bayesian statistics, did the proportional analysis, and we got these numbers. And I'll show you the graphs of these later, which is more interesting. Okay, so what did I break up so far? What did I talk about so far? I talked about hazardous and non-hazardous leaks. I talked about leaks that are leakers that make up those two, and also for the non-leakers about the non-detected leaks, if those non-leakers were 100 part per million or more. We also had other factors, other input variables like the facility or the operator. The facility is just saying, what type of meter is it? Is it a commercial meter? Is it a residential meter? The operator is who did these 425 and these 60 measurements. Well, we ran an analysis of variance, and I ran actually quite a few analyses, but ANOVA is beautiful for this because I ran the residuals on this entire project for the DFITS betas, for the Cook's distance, for every type of residual, and we had an excellent data set. The SoCal did a very good job, obviously, operationally having a quality data set. So ANOVA just tells you, do you see a difference between commercial meters and residential for the average leak rate in their distribution? So not only the average leak rate, but that distribution and the standard deviation around that average, how your data is spread. And the answer is no. The ANOVA says that it's likely it's not, there's no difference between them. And also for the operators, I'm going to show that graphically in a minute. We also, why is this important? Because of it's confirming lack of bias in the sampling process. So that's a human factor. Like, well, what if someone else took the measurement? Well, we found there's no difference in statistically meaningful sample size number that the ANOVA is telling us. It's like in a medical trial, was there any difference in taking this diet drug? No, you didn't lose any weight. I'm sorry. The ANOVA said it didn't work. Well, we didn't see any difference here. And it's for operational decision making, these extra things are important, even though we're not using them for the EF roll-up in this case. Okay, so here's by facility type. You can see commercial and residential, and that's for hazardous, and for non-hazardous. We actually had one industrial meter, but one doesn't do anything for you, right? It's just you don't really analyze that. We were looking at commercial and residential meters, and statistically, when you run the analysis, there's no difference in those groups. And here's the operators, 6 operators, numbered 1 through 8. They're not contiguous here for leakers, and a couple did the non. You can even see it here even clearly. Very, very not sensitive to the operator, if you will. Now I'm going to the other categorical metadata for those same leaks. Remember, we had the 425 and the 60? Well, we separated them by has and non-has, and by leakers and non-leakers, and I talked about it just a second ago about looking at them here by operator and by facility. Well, we also, Eric showed this picture, I'm gonna go back to it, and this is just one of foam, but every single leak had a bubble test done on it. And even when you think about what I'm gonna say here, even when you have a soap solution, which is called a surfactant, right? It lowers the surface tension of the water. That water can get in and clean the grease and dirt off your hands, and you can form bubbles. Well, even if you have a beautiful mix and the wind speed is steady and the wind direction is steady and you've mixed it properly and you've applied it the same way, then the cleanliness of everywhere you put that is different. And you know automatically, if you've ever washed greasy dishes, it's a lot harder to get bubbles forming than if you're washing somewhat clean dishes. And so this is very sensitive, this type of process of trying to categorize a leak rate, to the cleanliness, to the relative humidity, to the wind speed. It's much, think about it, just look at this. For these leaks, you're fully encapsulating it. You don't have to worry about mixing in soap with cleanliness. I've run studies on this. It's very hard to get a repeatable process. It just is. And we're going to show you that just statistically. Here you're measuring with a precise probe here, looking for the 100 part per million. Here you're encapsulating, getting everything. So let's go back to the bubbles and see what we found. What did we find when we ran that analysis, right? So here we go. What you find looking at I always like to show the raw data because you don't cheat on raw data, not that we would, but it's nice to see the raw data. I jittered these kind of like a violin plot, and you can see here that the little bubbles are foam. There's actual bubble size that's categorized digitally for bubbles, and you can see indeterminate. It means you had a leak, you had all these leaks that we found with the normal process, with the hazardous and the non-hazardous, but you couldn't form a bubble. There wasn't enough gas to push that bubble and make a bubble, or it was too dirty, or the wind speed was too high. And then there was 3 or 4 up here. I think there's 3 in this one. It's possibly, yeah, you can see 3. There's a double line there that were soap blown off. This is where, if you've ever had blown bubbles with your kids and you blow too hard, the bubble just blows off the little thing you're blowing on. And so what do you see here? Anyone can look at this and say, wow, our leak rates for bubbles totally encompass when we don't form a bubble for a leak, when we form a bubble for a leak that's foam, and when we form a bubble. And when we do form all these leaks that are the same size, it's like a 50-50 chance if they'll form a bubble or not. So, I mean, how do you separate that out and categorize your leaks? Well, you don't. I mean, you can claim it. It's even worse if you subcategorize these into other divisions. They overlap even more. And so you see that here, and we were open-minded. We wanted to use this, but you just can't do it with a straight face, at least for SoCal and using this on their property. I don't want to cast doubt on bubbles altogether, but this is what we found. It's just data. And you can see the ANOVA analysis on this was super clear. These are the same. There's no discriminating ability to see the difference between a leak that doesn't form a bubble and a leak that forms foam. They just look statistically the same. Just flip a coin. And then the bubbles encompass all of these. So if you have a leak between here and here, it really could be any one of these. You don't know. So to work backwards, good luck. It could be any one of these. That's not the case in the has, non-has. You have the clear separation. Just for good measure, we took all the non-detects and we grouped them into one category and then replotted this, and it's the same thing. So you not only don't know if you have if you have foam or you don't have a leak, but you don't even know if you have a non-detected or not using the technique. So that's the same on the bootstrap. I won't dwell on that. This is a really interesting slide. Everything I talked about, and I'm kind of getting towards the end. I just need a few more minutes here to wrap up the Monte Carlo after this. But pay attention here. This is really interesting. You've got a log scale and a log scale. You've got the leak rate and the leak concentration. I did not talk about leak concentration up to this point, okay? So here we're looking at the leak rates here, right? These are the leak rates, but these have been all categorical variables. So it's a categorical versus continuous plot. This plot is a continuous variable that ranges, because you know what this plot is? I'm gonna go back, I'm gonna take a second. It's this measurement versus this measurement. I bet that helps. It's the full leak rate on the same meter set versus the concentration on the meter set. And that's what this plot is. So, and then you take log. How do I know I'm going to cheat and go ahead? Here's the concentration. Concentration is beautifully log normally distributed. Beautiful. Just like the leak rate. This is part per million gas or methane, or whatever you use. The other one is standard cubic feet per hour. You can see it there, SCIF versus ppm. You do a linear regression because you got log data. And it's part, it's a textbook linear regression. I ran 500 other fits. Linear regression is the best fit because they're both log normal. And here's your regression solution is this red line. So if I have a 2.0 ppm, I expect 10 to the minus 2.8 skip, okay? So what is 100 part per million? You know, you can come into 100 part per million, it's 10 to the 2. You come up here, and that's what your leak rate is. And there it is right there. At 0.002, this red line, right, this 100 part per million is giving me this minus 2.69. That's what this 2 is, intersecting this red line. And guess what? On average, the regression is excellent. My confidence interval at 90% or 95%, I'm sorry, is really tight, and the residuals are equally spaced. But on any single leak, you've got a 2 order of magnitude. But if you were frankly, if you were reporting your emission factor based on concentration, on average, you're going to get the right answer. On each point value, you might be off, right? But that's what this is showing. This is really valuable for the industry, and it's going to help, like I said in that other slide, with operational decisions, because it's a lot cheaper to take a concentration measurement than a high flow sampler with enclosement, right? Okay, and this was just showing the concentration itself in part for the same lakes, the 425 and 60. You know, kudos for SoCal for capturing all this data. So now how are we going to take this data to get emissions? Not emission factor. I showed you the emission factors already for HAZ and non-HAZ and for the non-detected leakers and the proportion. How do you combine all that? Well, the only way to do that properly is to take your population data and your leak specific data like emission factors and proportions of samples with their full distributions like that you see here, and run a numerical Monte Carlo analysis. And what is a Monte Carlo analysis? You take your equation, you run your averages all through it, and you get an answer. But you want to know what the confidence interval is around your emission factors, or your emissions in this case. We did this already for the emission factors with a bootstrap analysis. Bootstrap analysis works off the data. Monte Carlo works off of a full distribution. And we have those distributions. And then you sample randomly from these distributions 100,000 times and get your answer 100,000 times. And you use this not to get the average off of this, you just use your averages for that, but you use this to get the confidence interval around your average using the Monte Carlo. And that's exactly what we did. This is key for this presentation. Why we are using hazardous leaks and non-hazardous leaks is defined by the PHMSA hazardous Part 192 categories, and Ed went over that in brief, and you can look that up in the report for more detail. And guess what? For 7 years, like Eric or Ed had showed, SoCal has 100% of the data for all their leaks. Remember, Ed showed they had 5.8 million meters in 2015. They're growing at about 0.5% or what have you. And so they grew from 5.8 million meters to 6.1 million meters over these 7 years. And the emission rates, the emissions went up because all the current EPA GRI process used was a single multiplier by your meter set. It's dumb. I don't mean that in a derogatory way, but if you're just multiplying your meter sets, but your leak rates could have gone way down. Right? And we're going to see that's exactly what happened, but we'll get to that. And so they know all of that. And in fact, look, SoCal grew as a company to 6.1 million meters. Their leaks went from 100,000 to 60,000 over those years. They're doing a better job. They're getting better and better every year. And we know how many days they leak on average. We know the proportion between them because we know every leak, and we know how many leaks we have and how many were leakers. This is population data. There's no uncertainty in this data. There is uncertainty in the emission factors, and now I'm showing this to you for the first time. I showed you the bars at 10 and 95. Here's the hazardous emission rate, the 9.8. Here's the 0.3, whatever it was for non-hazardous. Here's the 0.0085 or what have you it was for the non-detects. And remember the 29% of the ones they said didn't leak actually had 100 part ppm or more with the pencil probe at that 0.002 skip. So these are all inputs into your total emissions. You take your number of meters in each of these sets, the number of leaks, You multiply them by the correct emission factor. For the non-detects, you say, no, we really know 29% have a small leak on it, so you have to apply that percentage, and you do it as a Monte Carlo, and here you go. This is the output. This is the inputs with the uncertainty. Here's your 2015, 16, 17, 18, 19, 20, 21, 22. These are the total emissions. These are the total emissions. And you can see they're in MSCF natural gas. So we're changing a little bit here. These are typically done in natural gas, not in methane. And you can see, let's just look at 2015 here. So you're really going from, these red lines here are the 90% confident, the 10 and the 90% confidence levels. And that's typically what you put. You can put these at anything you want, but for a Monte Carlo, that's typically where you're going to put those. And this is and the most likely value is here. And we'll look at the averages on the next slide. But just look at this, 400,000 to 800,000 is our uncertainty. And look at our bandwidth. When you get down to 2019, after 4 years, this is like 300,000 to 600,000, possible. These are all the possibilities in the population it could be. And then these are tightening. It's moving. These are moving to the left and they're getting smaller. They're kind of oscillating back on this last one. You're probably getting towards an equilibrium, but we'll know more when we look at the 2023, 2024 data. So here's a look at, and I'm almost done now. I'm just a couple slides. Hang in with me. So here we look at the means. These are the means that if I would have plotted them on here, I didn't, it's too busy. And this is a stacked bar chart. So this is 605,000, which would be right here, real close to the mode. And down here, we're around just under 400,000, which is 392. So I just wanted to point that out. And we can look at these as the categories, the subcategories, were they hazardous or non-hazardous leaks or non-detected. And what you can see is their average emission, their emissions, total emissions is going down. And remember, it was predicted to go up. And we're going to see that on kind of the last slide next. And you can see the categories that are shrinking. The hazardous are going down, the non-hazardous are going down, the non-detects maybe not so much, relatively flat because you're just looking at how big their system was growing. And then as far as the unknown for the off years, and I'll talk about annual versus 3 and 5 year survey in my last slide. And so these are going down, and this kind of brings it home. Why did we do this study? Why did SoCal do this study? And go to an enormous amount of effort to do it right. This is what, without this process, without this company-specific leak-based emission factor process method, they would have reported their emissions went up. Even though they've done these Herculean efforts that I'll show you on the next slide to lower their emissions, they would have gotten no credit for that because this would have, and dare I say, it's an incorrect summary of what really the emissions are. This is just a multiplier based off of a national study that had a huge confidence interval, had very low precision, frankly, in some of, you can look up the references in the report, and you just apply that to the number of meter sets. It's just not a true measure of the emissions. This is what actually happened over 7 years. And this is based on everything I talked to you about. These are the average leak rates by year, and these are the Monte Carlo bands. And you can see it going down. It's somewhat stabilizing now. And you say, well, why did it go down? Well, I'll show you on the next slide. So this is population or facility-based emissions. This is company-specific leaker-based using hazardous and non-haz categories where they have 100% of the population data and no uncertainty in that category. And also doing their robust study for the non-detected leakers. So my last slide. This summarizes this slide, okay? So here we go, we've got what happened. We went from 2022, population, it would have went up 4%. Just like Ed showed, their meter count went up 4%, so their emissions went up 4%. In reality, it dropped 43%, and that's this drop right here. Why? Well, because they did things. Because you're in the state of California, and CARB and the commission are the leaders in the nation on that, and they are looking at getting emissions down. SoCal, in my opinion, is one of the leading companies in in really being green and lowering from, especially since I've been working with them, they're driving it. They've accelerated their non-hazardous leak repairs. So you're always doing a continuous cleanup of the hazardous. You just have to, that's a safety consideration. The environment gets the benefit of safety on that. But now they're accelerating the non-hazardous leak repairs. And they've increased their annual surveys. They had their annual surveys on their meter sets at 1, 3, and 5 years. They took those 3 years and they pushed them into 1-year buckets, and they got a 19% increase over this time frame. So what would have waited 3 years, now they were finding them in 1 year. They're driving this down here over these 3, 4 years. They're bringing it forward so you can see this slope go down. And then they brought in new technologies like an advanced meter estimation initiative, where they changed out meters and put a very advanced meter in to do measurements where they could quantify leak rates. And by doing that, they also accelerated, that these two are kind of joined, they accelerated the assessment replacements of their assets, and they modernized their facilities. This could be things like putting in less joints, threaded connections that could leak. So if you're changing out something, put less things in that could leak, right? Maybe 3 joints instead of 10 joints, because that's where your leaks are. They're in threaded connections or in the ERT on the meter face. They have a better design. And so they also implemented leak prevention programs. And so, you know, these are the things that led to this. If they would have just stuck with that you would have said, oh, you're not doing so great. Your rates, your emissions are going up, but no, they're actually going down. I'm going to turn it back over to Ed, and Ed will coordinate, you know, any questions. He'll help us so we can answer any questions you might have.
Thank you, Daniel, for your presentation and your words. And now we will open it up to questions, and we have a few questions that have come in. I'll go ahead and read the first one that we received. Daniel, the question is from Royo Jamarani. I see that he's left the webinar, but what is the benefit of a leaker EF over a population factor? Both company specific.
I was here the last 5 or 10 minutes, Ed. So I'll answer that again, even though I just said it. It is everything, you know, that of what I just said. If you look at the screen here, you see, if we just use the population base, all you're doing, I mean, let's look at it. SoCal is growing as a company, right? There's just more meter sets. It goes from 5.9 to 6.1. And if you just use a population base, you're just going to multiply that by a constant. And you're just going to, your leak rates, no surprise, go up at the same rate as how fast you're growing as a company, even though you're doing all 6 of these things over 7 years to lower your leak rate. So the benefit is it is an accurate portrayal of your emissions. The population base is not an accurate portrayal. It is just taking a national number with a national leak rate average. So it's a double whammy. You're not taking credit for things that you can measure, like has and non-has leak rate every year. And you're also just multiplying it by a national factor. When you use this whole process and you calculate these distributions like SoCal did, they have their actual leak rate. I'll end on that, Ed. It's very strong reason.
Yeah, and from a company perspective, you know, you want to make informed decisions as a system operator, right? And if you're using a factor that's kind of not leading you to really understanding what your system is doing, then you're not going to make good decisions as a system operator. And so if you really want to improve the environment and reduce your emissions, you need, you know, data that's realistic as to what your system is doing in terms of the emissions. And so that's a real benefit of going to a leaker-based emission factor, you know, because it's really informing the system operators so that they can be responsive to the performance of the system. Okay, the next question is from Fred Haynes. The has, non-has emission factors are more crude and subjective than bubble size EFs. Why SoCalGas does not use the later as a company-specific EF to have a more objective and accurate emission estimate from customer gas meters?
Well, I could take that technically, and then you can jump in operationally if that's okay. So I think I went through this. It's actually, I mean, I appreciate the question, Fred. From a statistical standpoint, it's actually the opposite of what you stated. And I did show that. If you want to go into the report, please download it, and you can look at the ANOVA analysis, analysis of variance. And this plot really, I like looking at raw data. I could look over here, you know, and just, I'll just start here. If we take the bubble sizes, there's 4 categories. You have a leak and you don't form a bubble. Those leaks could really be anywhere from 1, 2, 3, 4 orders of magnitude. Now you have the same leak that's somewhere in here. It could equally be likely to give you foam. And it actually, if you look at the numbers, there's a good chance it could also just give you bubbles. So if you're going to take you know, the soap blown off is really up high. I can't really say with certainty. There's only 3 there, but I'm pretty confident if you don't want to have a lot of these leaks as an operator, right? And that's good you don't have them. These are large leaks. So maybe this one would tell you, well, if I put soap solution on and it blows off, I know I've got a large leak. Well, the HAZ category tells you that anyways, and it does it reproducibly, and you have 100% of HAZ on your leaks already. It's already something operators are doing. So this does not give you the backward predictive power. Fred, you might look at it the other way, but if you're going to use bubbles to assign a leak rate, you don't have the speciation, the separation to do that. You do if you look at here. If you look at the HAZ versus non-HAZ, there's a clear separation. It's in fact not crude. It's in fact giving you pretty good tight bands because we made the sample size give us those precision bands. So it's not a crude measurement. It's clearly separated, and you don't have any problem going in the opposite direction, picking the wrong emission factor. The other thing I'll say is, if finally from an operational standpoint, you can see this is a lot different, and you just come in with a methodic way to put concentration down and put your full measurements down. This, and I have run other studies outside of SoCal and found the same thing. There is a huge amount of variability on what kind of bubble size you get, if you get bubbles, if you don't get bubbles, based on the shape of this. If you have an L, you have a notch. If you try to do this on a meter face with glass on it or that, and plus the cleanliness of this, who mixed the soap solution, how windy is it, and what's the relative humidity, and all of those give you less repeatability and less predictive power, even by the statistical analysis, than just breaking it into the hazardous and non-hazardous categories. I hope that answers the question.
So Daniel, I think, you know, if you think of this from a practical perspective, right, if you were to implement a bubble size strategy, and you looked at it from a system operator perspective, right, and you did that ANOVA analysis for our study, you know, showing that there was a little difference because of the overlap in the categories, right? You could get any kind of combination of data from all your different field employees, right? And that would drive a lot of uncertainty in the overall emission estimate because of the lack of the separation in the categories.
Correct. So let me just, I want to just, I like the way you said that, Ed, and I'll just say it very quickly here, very quickly. If we look at the bubble categories here, sorry, give me a second to get there. The only one you have the same type of separation on in the bubbles was if you blew the soap off or not. And that's only with 3 samples. You have a clear separation. You get this same separation with HAZ, non-HAZ. So that's exactly what you just said. You don't have the separation. You're trying to subdivide something, at least in our case and in other studies I've done, that it's hard to subdivide it. You're just getting statistically, you're just subsampling a larger distribution. And that's basically, for the technical folks, Ed said it clearer than me and simpler than me.
Yeah, and it would be very subjective basically for your field employees, right? And then from an emissions estimation perspective, because of that subjectivity between categories, you're going to get a lot of variation in your end result of the estimate of your emissions as a result. And this is actually something that was unexpected, right, for us in the study, that the has, non-has categories did have this separation from an emissions estimation perspective, which was a fantastic result for us because it provides a much better estimate of the emissions. And we didn't have to implement anything incremental, right, in terms of the categorization for our field employees. And so you get that consistency year over year in their practices, and it's less complicated for the field as well. So there's a lot of benefits operationally, as well as providing better emission estimates. Fred also had another question. How do your new has, non-has EFs compare to the old nationwide EFs to estimate a particular year emissions? How do you verify your new EFs represent the reality or close to it?
Right. I'll take a stab at that. And we actually didn't present that in the paper or in the report, but we're refining that methodology right now, if I can say, Ed. The way you look at this is each year you go in and you get a sample size that has statistical power of your leaks. And you look at that, you do the same analysis. I'm not going to go through it again. You do the same analysis that I just went over here, and you get your emission factor and you get the 95% confidence band around them. And then you just run. Some people are familiar, if anyone does any investments or things, there's something called a simple moving average, and you can have Bollinger Bands, you can have confidence intervals around that. And you can look year on year by doing what's called a Cone D analysis and also an ANOVA statistical analysis and say, well, look, I did all of my, and let's just say these that represent our emission factors. I don't have them plotted for every year. We don't have that plot, but if these were the emission factors versus the emission, and you said year on year, am I seeing a difference in hazardous and non-hazardous leaks from my random samples I'm pulling from those categories? You're literally doing a random sample every year on those categories. Then you're doing an analysis to say, do I have the same emission factor or did it change? Did it go up or down? And the way you do that, like I said, is you look at the variance between those sample sizes compared to your current emission factor, and you look at the difference between the averages, which is your Cone D difference. So you not only look at, did it go up or down year on year, but is the spread of the data, which is included in that, is it tighter or wider? And when you run that proper analysis, you get an answer quantitatively. Did I observe a change in my emission factor this year? And you get the answer immediately, and you can immediately update your emission factor if you meet that criteria, or you leave it the same. Why is that important? If SoCal were instance, I'm going to give you two scenarios. One of them is a happy scenario. They keep on doing these things and it keeps driving the emission factor down. Well, then you want to change it and get an accurate value, but you have that year on year. And by the way, you have the full population data that we showed here available every year to do that. Okay. The other scenario is, let's just say, and this isn't the case, but hypothetically, they have a particular union they put in, or a particular plastic stub pipe, and those start to leak for whatever reason. They hit the bathtub curve, and all of a sudden they start getting more leaks. Then in that case, when you do that analysis year on year, you'll see that emission factor go up or down. So this gives you the additional benefit that if something started leaking due to a wear-in, or it just takes time, you'll note that, change the emission factor, and you'll take action. You'll do the discovery and find it operationally. The current process doesn't do that for you. If you look at it here, you're still using the same emission factor from the national study. So just looking at it graphically, you might say, well, my leak rates went up, my number of leaks went up, but you don't know about the leak rate. So to put a period on it, it's an annual process, and you look at it with a non-biased, statistically meaningful sample, and every year you check the change and see if it statistically is worthy, both in statistically a worthy change, but operationally, like, is it really significant enough? And that's what a Code D does. In medical trials, that's the effect size for those people on the line that know what effect size is.
So to add to what you said, Dan, so you're kind of getting a window with what Dan said into kind of the next phases of the work, right? The results of this work has changed how SoCalGas manages our emissions, right? The annual sampling of our system to maintain our company-specific emission factors is being institutionalized into the organization, so that is an ongoing process for us moving forward in order to maintain these factors, in order to monitor the performance of the system. And so if something changes, good or bad, it'll be reflected in our sample, and we'll be able to make good decisions in terms of managing the emissions from the system. So thanks for that question. Let's see. Next question, and I gotta go back up. From Michelle Kennedy. Are these numbers a result of the distribution riser inspection project being implemented? So I'll answer that question. These are all leaks from the meter set assembly that are above ground leaks, whether it's from the riser below the valve up through the regulator, the meter, the service valve, up to the customer pipeline coming out on the downstream side of the meter. Zach Weller asked a question. Based on the results of the Monte Carlo analysis, the point estimates do go down over time. However, the uncertainty bands overlap quite a bit. Would it be correct to say that there isn't enough statistical evidence to definitively conclude that emissions are going down over time?
Can you repeat that last? He said that I just was catching the last.
So the uncertainty bands overlap quite a bit, he says. Right. And he asks, would it be correct to say that there isn't enough statistical evidence to definitively conclude that emissions are going down over time?
Yeah, that's a good question. So it depends on the gap you look across, right, Zach? So if you were looking at comparing 2019 to 2015, you would say yes. If you ran that, and I've run these analysis year on year, particularly with the emission factors too, not just the emissions, because now you have a larger separation, right? And if you run the ANOVA, this distribution is tighter at the same confidence interval, if you will, than this one. And the average value is significantly lower, right? It's almost, it's 50% lower here. But if you were to look at it, if you were to just myopically put blinders on and look at it from 2019 to 2018, you'd say, yeah, it went down a little bit. But no, you would say there is no statistical difference between 2018 and 2019. So I'm answering your question yes and no. It depends on how far back you want to look. So let me give you a scenario. You set your emission factors based on this. Let me pick something a little bit easy, more illustrative. Let's say your emission factors were set on the 2017. That was where you have them currently set. And you go to 2018, and it's just that we're refining that process, but when you get to the effect size and the P statistic, it's just borderline. Let's say it's 10, a P statistic of 10. It could be a 90% chance, versus a 10% chance due to randomness in your random sample. But the next time you go down here or here, you get the trigger value, and we're setting those trigger values statistically. Those are always set subjectively. What difference in a significance level and what difference in an effect size should we say we have a difference? So it might take a couple years for you to say oh, okay, I do have a change here, and then you pull the trigger based on what your current value is. Or it might happen quickly, like between 19 and 20, and you say, well, we did a lot of work, we replaced a lot of the system, and it drops here. So the answer is that's baked into the process we're working on, where you're looking, and that's why I kind of hinted, you can look at it year on year, and you can look at it as a moving average, which dampens 1 year that might go down, right? That's why a moving average is great in financial analysis, because you don't want to say there was some Federal Reserve, the chairman, said some word and everything dipped, and then but it went back up. So by using a moving average, or even a series of a couple moving averages, and like a Bollinger Band, you guys can look that up, which is like 1 or 2 standard deviations off that, you can quantitatively say with a confidence level when I've had a change. So it's actually quite simple to do once you set up your moving average and your bands. And you just look, when do I get out of that band or not? Any other questions?
Thank you, Dan. I'm looking to see if we have any hands up. It looks like Christian has his hand up. Christian, I've unmuted you if you want to. I see that you have a question in the chat, Christian, and I will answer that question real quick. But he says at the CPUC Winter Workshop on February 1st, 2023, SoCalGas confirmed that there were 79 non-detected leaks found by the R&D team, but the SoCalGas study only disclosed that there were 60 non-detected leaks. Will you please explain why SoCalGas decided to disclose that the company threw out 19 data points in the MSA study, which would have resulted in an increased false negative rate? So that is tied to the 100 ppm threshold. And Dan, I don't know if you recall this, but we did have some non-detected measurements that were below the 100 ppm threshold. And just as a reminder, the 100 ppm threshold was a threshold that was set by the CARB study, where they measured MSA leaks from SoCalGas, PG&E, and SDG&E. And that threshold was also used in other prior studies. I think New York also used the 100 ppm threshold in a prior study. And of course, when you get below 100 ppm, the emissions are lower, right? We have the linear regression showing that. And so if you were to study emissions from the MSA that were below the 100 ppm, you would end up with another emission factor. But in order to keep the data consistent across the studies based on that previous threshold that was established for California at the 100 ppm level, which made sense from an emissions perspective, that's why we made that adjustment. Did you want to comment additionally on that, Dan?
Yeah, I could, and you did a good job, Ed. So I'll make it quick, but it's let's just go back and look at this rail. So Ed was talking about it. That was down here. Here's 10 and here's 100, and you could bring this down a little bit more. But if you want to set that criteria, you could have brought this back to here, and then these leaks will start being part of that comment, like if it was shown. So maybe at that point in time, we included these leaks here, but like Ed said, to be consistent, this is an arbitrary 100 part per million that really had no basis in scientific basis at the time until we ran this regression. I'm not aware of any correlation of this quality. So we literally now know what that 100 part per million means. And if you actually look at, let me just swing over to this. This is the hazardous. If I go to the non-detect, so what Christian's talking about is you have 425 leaks here, And then what operations says doesn't leak are here. And if we added in the 19 more that weren't at the 100 part per million, but let's say they were at a different value, that would add inside of here. It's not going to change this. It's going to, you know, potentially bring it up a little bit or down a little bit, but that was just set at the 100 part per million, which is what is the prior in the CARB. And actually, I had a CARB project as well. And so that's why that's there. Is it going to cast a difference? Maybe minusculely, but what you recall my previous answer, every year you're taking samples. That's the beauty of this process. So every year you're taking samples. So every year with this process, you get the has and non-has ratio. And then also you can add into, and this is to answer Christian's question, a little bit additional bonus material. You can add into this Bayesian analysis the next time you have, if it's a leaker, is it 100 or not? And all of a sudden, this is going to go up over time to 400, 500. You create your error table for that, right? I'm calling it an error table, but it's only one proportional number. And then based on, if you let me go here, give me 2 seconds, find the Monte Carlo inputs right here.
Dan, I think Christian wanted to clarify his question.
Oh, okay.
Christian, I've unmuted you. Can you speak now?
Thank you, Ed. Can you hear me?
Yes.
Yes, Christian, I can hear you too.
Thank you. I just want to make sure my question was clarified, because at the winter workshop, one of the authors of your study stated that the 19 data points were not used because they were determined to be associated with all damages or for some other reason. The reason was never given that these leaks were under 100 ppm. So I'm wondering, why were these 19 leaks not used? Because they were never explained that they were under 100 ppm. They were explained that they were associated with all damages, or you couldn't get a good reading on them. So I'm just saying that the explanation you're giving right now, it completely conflicts with the explanation that was given at the winter workshop last year on February 1st. It's recorded, so you're more than welcome to go watch that explanation. But I just need to point out that it wasn't given that they were under 100 ppm.
Thanks for clarifying that, Christian. We'll go back and verify that was the case. If it was related to a damage, of course, in the data we treat damages differently. These leaks are leaks that are found on survey. So we will clarify that for you.
Okay.
If I misstated the root cause of why those were not included in the study, we'll double check that.
But the actual question was, why was this not disclosed in the study? You know, in most studies, when data is not used, it will be explained why the data is not used, and this was not mentioned at all.
Yeah, like I said, if they're not leaks that should not have been included in the study, then that's why they were not included. You know, based on the structure of the way that we report emissions within the SB 1371 framework.
But in the study, there were leaks under 100 ppm that were included in your data set.
Well,
like
I mean, look at it, there's 206 samples, right, Christian? And those are all of the leaks that, let's take a step back, because we're talking about a bookkeeping issue. I want to separate out the technical from the bookkeeping. And if you look at it, let's start one step above. So you have leaks that operations says are leaking, and they're leakers, right? And there's no issue there. They are leakers. They're leakers. And then they say, okay, we've surveyed and we didn't find any leaks. So then R&D goes behind them and does a precision measurement, you know, with the pencil probe, if you will, the one that Eric showed, and says we did 206 random samples where operations went through and said we didn't find a leak. And of those 206, these were 100, there were 60 that were non-detected, and they were included in this study because they met the functional category that Ed's saying. And if it was stated differently, the reason behind that, but the part that's saying that I was saying that it's below 100 part per million, well, that's 206 minus 60, right, Christian? That's the ones that we did 206, and you take 60 off of that, and that's your non-leakers. The part that if they made it at all into this bucket is what you're talking about. So Ed can reconcile that and say, oh, well, that's not even part of how we were categorizing this. You know, that was due to a mechanical damage or something. I don't know if it happened before or after when operations was there. He can sort through that and get back to you. But I want to make it clear to the audience, and the paper is quite clear, these were 206, and then the ones that were considered non-detected were the ones that were at this somewhat arbitrary level of 100 part per million put here. And the other ones less than 100 were here.
It's also important to keep in mind that this study went through a lot of rigor with at least 2 peer reviews. And so there was a number of things that were addressed throughout the study to provide the best study possible. We will address your comments, Christian, and get back to you on that data.
Okay.
I think Fred also had a question, and we're wrapping up. We got to wrap it up here. So Fred, do you want to ask your question?
Ed, I don't know how my questions and myself being identified as Fred. I use the link Fred sent to me.
Gotcha.
That's probably the case. Okay, so I just want to declare the 2 questions that I have earlier that you read as if coming from Fred, they were from me.
Okay, thank you, Win. And that's Win with Carb.
I win.
Fred,
Thank
do you have your hand up?
Perhaps I had done them in my sleep or something, and but appreciate you clarifying that you had asked those questions, but they appeared to be coming from me. Thank you, Wayne.
All right, well, I think we're gonna have to wrap it up. We're over time. I did want to share on the presentation the last slide here. Show my screen. Yep, okay. So thank you all very much for attending. We appreciate your participation and your questions. It helps us all improve as we hold these webinars and get the input from our stakeholders and those involved in the work. We've included our another QR code there for our RD&D website and our contact information for our speakers. Dr. Lamb did not participate, but he's been online and he's heard the conversation. So I thank Dr. Brian Lamb for his involvement, and unfortunately we ran out of time, but thank you all for your participation, and this will conclude the webinar, and hope you all have a nice day.
Thank you, Ed.